Hi, this is Rick. I want to talk a little bit about VSEPR, or something we call valence shell electron pair repulsion theory. So this video is, I'm going to try to keep it as brief as possible. It's going to have 4 parts. The first part is we're going to talk about what it is. So that this is a global, so the 2 first things are global, high level pictures of what's going on. So what it is and how do we use it? Like basically why is it useful? And then we're going to give some visual examples without any practice problems, just kind of show you around a little bit, and then we're going to actually do a couple problems so that you can see how to apply this in your homework. So first of all, what is valence shell electron pair repulsion theory? It is a way to help you envision what molecules might look like. So this is in opposition. There's another way to do this this is called valence bond theory. There's another way to do this called molecular orbital theory. And whenever there's 2 ways of doing something, you normally automatically think, well, which one's better and why use one versus the other? And in chemistry, it almost always comes down to simplicity versus accuracy or usefulness. So our valence bond theory is only good to molecules up to a certain size, and the molecular orbital theory, where you have to do some very more complicated things and even comes into quantum mechanics, is much more accurate. But we won't cover that in this class. We just do this one way. Now, why might you want to know the shape or have some concept of the shape of a molecule? Well, the shape of a molecule combined with the polarity information that we talked about previously helps you understand some of the properties of a molecule. Properties are things like its boiling point and its maybe even its packing density, and its other forces that are at play that help you understand how a molecule might react are related to its shape. That's an easy way to predict these things. For example, if you're in green chemistry, you might use some of a molecule's product to say, let's say you're making a new cleaner, and let's say that cleaner cleans engines for cars but kills ducks. Right? Maybe you can identify the part of a molecule that has a property that kills ducks, and maybe you can identify the parts that clean an engine, and maybe you can design a new molecule that doesn't do that. So it's also really important in drug discovery. There's these things called enantiomers, and there's these left and right-handed molecules, and how they shape and how proteins fold is all beyond the scope of this class, but they are fundamentally related to the individual properties of bonds and therefore of molecules. Obviously, we're not going to get there that far, but we're going to do things like, if you can see here, we're going to talk about linear. This is called trigonal planar. This is called tetrahedral, trigonal bipyramidal, and octahedral. We're going to go up to sort of that sizes. And we say things have lone pairs or charge clouds for things that surrounding a central atom. So things that don't have a central atom, this is not as useful for. This central atom is this sort of a red dot there. And I'll just scroll through some pictures of these things so you can see what we're talking about as some examples. So you have to pick the thing that there's the fewest of is most often the central atom. And you have a bond pair of electrons if there's an atom connected to it. But we need to make allowances, even though we don't often draw them, that these extra electrons called a lone pair have to live someplace, and they end up taking up more space than a lot of times the bonded atoms do. So we have to sort of accommodate for where they are. Here's some of these shapes. This one's called linear, in which there isn't a central atom, just a side one. This is also called linear. This is trigonal planar. This is bent. We say that this is bent because it has 2 of these green charge clouds here. This is tetrahedral. It's a tetrahedron. Trigonal pyramidal, trigonal bipyramidal, and octahedral are the shapes we're going to look at the most. And I'll go through a couple of examples here. So this is CO2, beryllium fluoride, beryllium chloride. These are linear molecules. I'm going to go over these quickly. We're going to do some other examples. You've got BF3, NO2, methane, CH4. You've got ammonia, NH3. You've got H2 and H2S are both bent, because you're only looking at the shape of the things that actually have an atom on it that say it's bent. These are just some quick examples, and I'll show you some 3D models of examples here in a moment, and then we'll do some problems. So let's go on a tour of a few examples. So I'm taking you to webbook.nist.gov, which is one of my favorite chemistry resource sites. It's real plain. It's not real fancy, but it's one of my favorites. So we're going to start with a couple linear examples here. I just want to show you these molecules in 3D so you get some idea of what these look like. This is a visual tour. I'm going to pick CO2, which I happen to know to be linear. And this is what CO2 looks like. We've got this central atom here, which is carbon, and we have two oxygens on either side. So this is what we call two charge clouds. A charge cloud can be a bond or a lone pair, and this is what this guy looks like. That's one example. Let's do, and I don't know that this one's in there, but we'll go with hydrogen cyanide 2 is another linear molecule, but that one has a triple bond in it. And so we're going to go with HCN, and we're going to take, yep, there we go. And let's see if we can find the 3D modeling. Oh, this does not have 3D model. Let me see if the isocyanate one does. Right, here we go. This one is linear. So we got this one here is another linear molecule. Not quite what I was looking for with the triple bond, but it is also linear, isocyanide. So there's a hydrogen, a nitrogen, and a carbon. So the nitrogen's in the middle, there's a carbon, and there's a hydrogen on the linear, but two charge clouds. They call it again. Charge cloud means it could mean lone pair of electrons, and it also could mean a bonded atom. So obviously linear, I don't have to tell you, is 180 degrees angles. So we're going to look at a few other ones. We're going to go to formaldehyde, which is HCHO, and this is what it looks like. So formaldehyde is right here. So there we go. So there's a C in the middle. We've got an O and O, all right, H and an H and an O at the top. So this is what it looks like. So this is kind of flat. You see how it's flat? And the bond angles are not quite, they're not, you would think that they'd be a third of 360 degrees, but you'd be wrong. You'd think they'd be 120 a piece, but they're not. So the bond angles here are 122 degrees, and here they're 117 because this guy it takes up more space and is pushing these down. There's some forces here pushing that down. So in this particular one, there are this is a trigonal planar molecule, just so you know, and they're normally 120 degrees. So if you said 120 degrees, it would be okay. It's close enough, but they're not quite 120 degrees just because of the differences in size. And let's look at some more here. Let's look at something that would be trigonal planar, except it has a lone pair on it. It's going to be SO2. Let me see if this is in here. I hope so. So here we go. This is SO2. Now what you can't see here, which isn't drawn, and I wish it were, is that there's one extra pair of electrons up here where you can't quite see. And this is a 120 degree angle down here on the bottom. And that's the top view. Here's kind of a side view, and we call this molecule as bent. There you'll see that there's more than one bent. But this is one of the bent molecules. And this gives it an overall polarity about this axis. So about here, you'll see that there's a difference in polarity. Later, we'll learn this stuff. We've got to continue, and that's the 3 charge cloud critter. The 4 charge cloud one we're going to do next is going to be the classic one, is the carbon tetrahedron. So we're going to say methane, which is CH4, and you'll see a shape one here. Let me see. This is tetrahedron. So these are all 109.5 degrees every angle between the other one. This looks like the playing jacks you had when you were a kid, or a caltrip if you're into military warfare. And this is what looks like carbon in the middle, 4 H's. That's what this guy looks like. That is a tetrahedral molecule shape. Something that would have been tetrahedral, but we call it trigonal pyramidal instead because it's missing one thing is ammonia. So we'll look here. I'm pretty sure ammonia is going to be, whoops, I didn't do it right. Ammonia, let's put you in here. Ammonia, here we go. Ammonia looks like this. So ammonia would have been a tetrahedron, but there's a charge cloud up here. There's a big cloud of electrons which bends the other guys down. So this is nitrogen and these are 3 hydrogens. This is what it looks like. So These are 107 degrees because as we've already learned, the charged clouds tend to push, especially the smaller atoms, down further towards away from themselves, and so that's what ammonia looks like. And we're going to do another one that ends up being bent, which is water. I'm absolutely positive water must be in here, so I'm not even going to worry about it too much. But water has two imaginary charged clouds. Imagine one coming up here, let's say to the right, and here to the left. It's kind of completing the tetrahedron in your imagination, but this is what water looks like. Water has 104.5 degrees. It's even squished even more because there's two charged clouds. Water is bent. Now you may remember that sulfur dioxide was also bent, but it was bent at 120 degrees. These are bent at 104.5. It's bent in a different way because the sulfur only had 3 groups in it, and this water has 4. There's 4 charged clouds here. When I say groups, I mean charged clouds. And then we're going to go to 5 charged clouds, which is we have a trigonal pyramidal. And I'm going to pull back on some of the examples a little bit here. So I'm going to say PCl5, so phosphorus pentachloride. All right, little buddy. And this is what this one looks like. So we say this has 5 charged clouds because there's 3. The center axis is here, and there's 3 that go about it, and there's one top, one bottom. It's called trigonal bipyramidal because you can imagine 2 trigonal pyramidal, 2 3-sided pyramids, one on the top and one on the bottom, and that's what that looks like. The others that I would give you examples of look just like that too. Yeah, it's bonded to each. It's bonded to all of these are bonding pairs. But if we see something that would have been trigonal pyramidal but it's missing one, that is, I'm going to give you SF4 as an example. So SF4. Okay, so sulfur tetrafluoride, this is called. And this is just like that, except it's missing one. Can you tell which one it's missing? Right, there's one that would have been sticking out right here, but it's a lone pair. But notice how these are kind of angled back a little because they're pushed back from that shape. So this would have been a trigonal pyramidal, but it's missing one. So we say it's shaped kind of like a seesaw. We say because if you look at it like, let me try to get this straight here for you. If it's shaped like this, we say this is a seesaw shape, but it starts off as trigonal pyramidal. And then the last one is ClF3 if it's missing 2, and it would have been trigonal pyramidal. It looks kind of like, whoops, did I do it wrong? I did ClF3. Well, it's maybe not in here. Chlorine trifluoride. Let's see. No, it does not have. There's no model data. All right, so let's do a practice problem. You'll find that these problems aren't too hard at all. Once you get it down, there's no math. You just have to have a little table or memorize a couple things. So the example is using VSEPR, valence shell electron pair. Whoops, I think I spelled VSEPR. It's okay. Predict the shape of bromium pentafluoride. So here's what we do. First thing we do is we draw an electron dot structure of this compound, and there's tons of videos on that, or I can show you how to do it too. So you draw this electron dot structure and you identify the number of charge clouds. This is the one elusive part of it. So the charge clouds are going to be 1, 2, 3, 4, 5, 6, because this means lone pairs or bonded atoms. So the next thing you do is you say the central bromine atom has 6 charge clouds. And so then we just look this up in our little table here. So this table is tiny in my screen. I'm going to try to resize this so you can see it more easily and make this a little bigger. And you can see that if we have 6 electron groups, that it is octahedral, and these are the angles that we have. So it's an octahedral arrangement, but it's not really going to look octahedral because we're missing the bottom one. So the actual shape we're going to see is, so we're missing this bottom part, right? Let me see if I can draw this right here. We're missing this bottom piece, or I guess it could be the top one too, but we don't have it. So we're going to look a little, it's going to be square pyramidal. So the basic shape is octahedral, but we're sort of a subset of that. So here's what we're going to draw. So we have bromine, and up here we're going to have a fluorine, and we're going to draw, this is how I draw a fluorine going back like that, and a fluorine coming out like this, and then going back like that, and then sort of coming out like this, and then we have a lone pair of electrons in the bottom, and I'm going to highlight that kind of a lightish green color so you can see it a little easier. This is that charge cloud there. So that's the basic structure of it, and the shape, I'm going to try to draw the pyramid here. I'll pick a different color for you. How about orange? This is going to be where my challenges come in here artistically. This is the square part of it, and this is the pyramid part of it. So I'm drawing a square pyramid. Can you kind of see that a little bit? That's the shape of the square pyramid that I get from this. If this were a fluorine, so let's take, for example, I go in here and I erase this bottom part, and this was a fluorine on the bottom. Let's just play what if for a moment. This were another fluorine, this would be octahedral, because then it would have, and I'll draw this other one in a different color. This isn't a highlight mode, so I don't overwrite myself too much. You can see that we would have another, yeah, it looks terrible, but there would be two square pyramids on top of each other. That would be octahedral. And again, I got the main shape of it from the 6 charge clouds and there's 0 lone pairs. If you see another chart that has 1 lone pair on it, it'll have that in here. There's lots and lots of charts that show this, so those charts are going to be your friend. But it also just makes sense that that's the shape of it. So that's the part that I wanted to get across to you. So there it is. There's a quick intro to VSEPR theory, and I hope you enjoyed it. Take care. Bye-bye.